What if I told you that sharks are older than trees? It's a mind-bending fact. You may have heard the idea that sharks were swimming in our planet's oceans long before the first forests ever grew on land. But is the story really that simple? The truth is far more complex and reveals a hidden connection between these two great survivors, a story of how the triumph of trees on land triggered a catastrophe in the sea, an apocalypse that sharks managed to survive. The statement "sharks are older than trees" has become a popular piece of scientific trivia, capturing the imagination with its juxtaposition of a familiar predator and the seemingly timeless nature of forests. This claim evokes an image of sharks as ancient, unchanging relics, swimming through primordial seas long before the first forests greened the continents. This report seeks to move beyond the simple factoid to investigate the deep evolutionary histories of both sharks and trees, using this captivating assertion as a gateway to a more profound understanding of deep time, the nature of paleontological evidence, and the intricate, often surprising, connections between life on land and in the sea. Sharks are frequently labeled living fossils, a term that speaks to their incredible resilience and ancient lineage. The group to which they belong, the cartilaginous fishes or chondriches, has an evolutionary history stretching back over 450 million years. Throughout this immense span of time, they have weathered 5 major mass extinction events, including the cataclysm that ended the reign of the non-avian dinosaurs. This remarkable record of survival makes the Elasmobranch lineage, which includes sharks, rays, and skates, one of nature's most enduring evolutionary success stories. However, the simplicity of the older than trees claim belies a complex scientific reality. The answer to this seemingly straightforward question is contingent upon definitions. What, in the context of deep time, constitutes a shark, and what constitutes a tree? This report will dissect this claim by meticulously examining the fossil evidence for both groups, exploring the scientific debates surrounding these definitions, and ultimately revealing a far more intricate and fascinating narrative. The journey will take us from the earliest microscopic scales in Silurian seabeds to the planet-altering rise of the first great forests in the Devonian, uncovering a story not just of precedence, but of profound ecological interaction and parallel evolutionary sagas. Reconstructing the evolutionary history of sharks is a formidable challenge, dictated by the very nature of their biology. The story is pieced together from a fragmented and often elusive fossil record, a testament to the deductive power of paleontological science. The primary obstacle in tracing shark lineage is the composition of their skeletons. Unlike bony fishes, osteochees, and terrestrial vertebrates, sharks possess skeletons made almost entirely of cartilage. While strong and flexible in life, cartilage decomposes relatively quickly after death and rarely mineralizes to form fossils. Consequently, complete, articulated fossil skeletons of ancient sharks are exceptionally rare finds. This fossil filter means that the vast majority of our knowledge about early sharks comes from their most durable, mineralized parts: teeth, dermal denticles, the small, tooth-like structures that make up their skin, also known as placoid scales, and the stout spines that supported the dorsal fins of some ancient species. Shark teeth, in particular, are some of the most common vertebrate fossils found. A single shark can shed tens of thousands of teeth in its lifetime, and this continuous deposition over hundreds of millions of years has left a rich, albeit incomplete, library of dental evidence. This reliance on isolated parts forces paleontologists to reconstruct entire animals and their evolutionary relationships from what are essentially scattered clues. The very earliest hints of the shark lineage predate any teeth or skeletal remains. They appear in the fossil record as microscopic scales. The oldest potential evidence comes from the late Ordovician period, with shark-like scales found in Colorado dating back approximately 450 to 455 million years. However, the identity of these fossils is contentious. The scales differ in some respects from those of modern sharks, and crucially, no teeth from this period have ever been found, leading some scientists to speculate that these earliest shark ancestors may have been toothless. The first undisputed evidence of chondrichians appears in the early Silurian period, around 420 million years ago. These fossils, found in Siberia, are isolated scales belonging to an ancient shark known as Elagestilopus. Each scale measures less than a millimeter long, and while their characteristic tooth-like structure confirms they belong to a shark relative, they offer no clues about the animal's overall size or shape. This sparse fossil evidence aligns intriguingly with data from molecular genetics. By comparing the DNA of living sharks and their closest living relatives, the chimeras also known as ratfish, scientists estimate that these two lineages diverged from a common ancestor approximately 420 million years ago. This creates what is known as a ghost lineage, a significant period in which genetic evidence tells us a group must have existed, but for which we have no complete body fossils. The tiny scales of Elagestilopus are the faint physical traces of this ghost lineage. They provide critical confirmation that the ancestors of sharks were indeed present in the Silurian seas, even if their full forms remain shrouded in mystery. The Silurian and subsequent Devonian period were transformative times for vertebrate life, rightly earning the title Age of Fishes. During this era, two critical evolutionary innovations appeared in the shark lineage: jaws and teeth. The evolution of jaws was a revolutionary development, transforming vertebrates from bottom-feeding scavengers into active predators. For decades, a significant gap existed between the molecular estimates for the origin of jaws and the oldest physical fossils. Recent discoveries have dramatically narrowed this gap. In 2019, paleontologists in southern China unearthed a trove of exceptionally preserved fossils from a 439-million-year-old Lagerstätte deposit. Among them was Fanjingshania renovata, an ancestral shark relative with a fully articulated jaw, providing the oldest definitive evidence of this crucial structure. Following the appearance of jaws, the first confirmed shark teeth entered the fossil record in the early Devonian, about 400 to 410 million years ago. These belong to a mysterious shark named Lenodus, known only from its tiny, two-pronged teeth, which were less than 4 millimeters in length. Later in the Devonian, more complete fossils begin to appear, such as Cladoslake, a 1.2-meter-long predator from around 400 million years ago that possessed many recognizable shark-like features. Yet even here, the evolutionary path is not a straight line. Detailed analysis of Cladoselich's anatomy has led some paleontologists to suggest it may be an evolutionary side branch, perhaps more closely related to the chimeras than to the direct ancestors of modern sharks. This highlights the great degree of experimentation that characterized early Chondrichian evolution. The period following the Devonian, the Carboniferous, is known as the Golden Age of sharks. It was a time of incredible adaptive radiation, where the shark lineage exploded in diversity, giving rise to a dazzling and often bizarre array of forms. This era saw the evolution of sharks like Stethocanthus, famous for its strange, anvil or ironing board-shaped dorsal fin, which may have been used in mating displays, and the family that included Helicoprion, renowned for its formidable spiral of teeth, often called a tooth whorl. The existence of these strange and highly specialized sharks powerfully refutes the simplistic notion of sharks as unchanging living fossils. The popular image of a shark is overwhelmingly based on the modern, streamlined predators like the great white survivors that represent just one successful branch of a vast and varied evolutionary tree. The fossil record of the Carboniferous reveals that the history of Chondriches was not one of evolutionary stasis, but of radical innovation, widespread experimentation, and frequent extinction. These ancient fossils are crucial for understanding that the path to the modern shark was not a direct march, but a meandering journey with many now extinct side branches. The direct ancestors of the sharks we see today, members of the superorder Selachii, appear much later in the fossil record. While some possible fossils extend back to the Permian period, the first confirmed modern sharks are known from the early Jurassic, around 200 million years ago. One of the earliest known members of this modern group was Paleospinax, a dogfish-like shark that had key modern features like a calcified vertebral column and an underslung jaw. This marks a gap of over 200 million years between the first Chondrichian scales and the emergence of sharks that are anatomically recognizable as modern. While the ancestors of sharks were diversifying in the oceans, a revolution of equal magnitude was beginning on land. The emergence of trees and the formation of the first forests would fundamentally reshape the planet's geology, climate, and the course of evolution itself. To compare the timelines of sharks and trees, it is first essential to define what a tree is in a paleontological context. Unlike shark, which refers to a specific taxonomic group, tree is not a single, unified lineage or clade. Instead, the tree habit is a convergent evolutionary strategy, a growth form characterized by a perennial, woody trunk that increases in girth and height, allowing the plant to outcompete its neighbors for access to sunlight. This strategy has evolved independently multiple times throughout plant history in unrelated groups, from ancient lycophytes to modern flowering plants. Therefore, when searching for the first tree, we are searching for the first fossil evidence of a plant that adopted this specific body plan. The evolutionary journey toward trees began with the colonization of land by the first simple vascular plants during the Silurian period. Among the earliest pioneers was the genus Cooksonia, which appeared around 425 million years ago. These were small, unassuming plants, typically only a few centimeters tall. They had simple, branching stems with spore-producing organs at their tips, but they critically lacked the key features of true trees. They had no leaves, no true roots, and no wood. These humble plants were the foundational precursors, the essential first step from which the world's forests would eventually arise. Early in this period, some plants began to experiment with height. By the Middle Devonian, plants like Eospermatopterus were reaching tree-like sizes of over 25 feet, but they still lacked the true, strengthening wood that defines a modern tree. They were proto-trees, an intermediate step in the evolution of the arboreal form. The breakthrough came in the late Devonian. The oldest fossilized forest discovered to date was unearthed in Somerset, UK, in sandstone cliffs dating back 390 million years. The forest was composed of trees called Calamophidon, which resembled slender palm trees with thin, hollow trunks. They had no leaves but were covered in twig-like structures and shed their branches as they grew. Shortly after, around 385 million years ago, a truly revolutionary plant appeared, Archaeopteris. This extinct genus is widely considered the first modern tree. It possessed a suite of advanced adaptations, including a strong, woody trunk that could grow up to 1.5 meters in diameter and support a height of 80 feet, an extensive and powerful root system, and large, fern-like leafy branches optimized for intercepting sunlight. Though it reproduced with spores like a fern, its anatomy was so advanced that it is classified as a progymnosperm, a crucial evolutionary link between primitive spore-bearing plants and modern seed-bearing plants, gymnosperms. With its global distribution, Archaeopteris formed the first widespread, dense, multi-layered forests on Earth. The rise of Archaeopteris forests was not just a botanical milestone. It was a planet-altering event with profound and far-reaching consequences that connected the fate of the land to the fate of the sea. First, these vast new forests began to act as a global thermostat. Through photosynthesis, they drew down immense quantities of atmospheric carbon dioxide, sequestering the carbon in their wood and in the soil. This dramatic reduction in greenhouse gases is thought to have triggered a period of global cooling. Second, the evolution of deep, powerful root systems fundamentally changed geology. For the first time, plant roots penetrated deep into the ground, breaking up rock and accelerating the process of soil formation. These root networks also stabilized riverbanks and landscapes, reducing erosion and altering the way sediment was transported across continents. This very success on land, however, had a catastrophic effect on the oceans. The aggressive weathering of rock by tree roots released an unprecedented flood of minerals and nutrients, such as phosphorus, into freshwater river systems. This nutrient-rich runoff eventually poured into the coastal seas. This sudden influx of nutrients is theorized to have triggered massive, ocean-wide algal blooms. As these enormous blooms died and decomposed, the process consumed vast amounts of dissolved oxygen, creating widespread low oxygen or no oxygen dead zones in the marine environment. This environmental catastrophe is strongly linked to the late Devonian mass extinction, one of the big five extinction events in Earth's history. This event devastated marine ecosystems, wiping out many species of reef-building corals, brachiopods, trilobites, and fish, including many of the early armored placoderms. This reveals a powerful and destructive feedback loop. The evolutionary triumph of trees on land directly contributed to a mass extinction in the sea, the very environment inhabited by the ancient sharks, which were among the survivors of this global crisis. The timelines for sharks and trees are complex, marked by different key evolutionary milestones. This complexity reveals that the popular claim sharks are older than trees is not a simple matter of fact, but a question of semantics. Its validity depends entirely on which shark and which tree are being compared. The heart of the debate lies in the ambiguity of the terms when applied across hundreds of millions of years of evolution. Based on the fossil evidence presented, there are several scientifically valid starting points for each lineage. For shark, the term can refer to the earliest Chondrichian ancestor, represented by the first disputed shark-like scales from the late Ordovician, approximately 450 million years ago. The first jawed shark ancestor, embodied by Fangingshanea renovata from the early Silurian, approximately 439 million years ago. The first toothed shark, represented by the teeth of Lenodus from the early Devonian, approximately 410 million years ago. The first modern shark, a member of the superorder Selachii, appearing in the Permian-Jurassic, approximately 250 to 200 million years ago. For tree, the term can refer to the first vascular land plant, the precursor Cooksonia from the Silurian, approximately 425 million years ago. The first prototree, a plant achieving tree-like height but lacking true wood, like Eospermatopterus, from the Middle Devonian, approximately 395 million years ago. The first true tree, a plant with a woody trunk, represented by Calamophyton or Archaeopteris, from the late Devonian, approximately 390 to 385 million years ago. By comparing these different valid starting points, we arrive at several different and seemingly contradictory conclusions. Case 1. The claim is true if one compares the earliest evidence for a shark ancestor, the 450 million year old scales, with the first evidence of a true tree, the 390 million year old Calamophyton forest. Then the shark lineage is indeed older by a remarkable 60 million years. This comparison, using the broadest definition for shark and the most specific, functional definition for tree, is the basis for the popular factoid. Case 2. The claim is false if, however, one compares the first modern sharks, Selachii, with the first true trees. Then trees are substantially older by more than 100 million years. This is a common and equally valid counter-argument that emphasizes the vast evolutionary distance between the earliest shark-like ancestors and the animals we recognize as sharks today. Case 3. It's complicated. The nuance becomes clear when comparing other milestones. The first toothed sharks still predate the first true trees, but by a much smaller margin. The first jawed shark ancestors are older than the first vascular land plants. The timelines are not perfectly parallel. Each lineage hit its key evolutionary benchmarks at different moments in geologic history. So in the end, are sharks older than trees? The real answer isn't a simple yes or no. It's a story that depends entirely on definitions, what we consider the first shark versus the first tree. But the most fascinating part of this story isn't about who was first. It's about connection. It's about how the rise of forests on land caused a mass extinction in the oceans, a crisis that the sharks endured. They are two of Earth's ultimate survivors, ancient lineages that have weathered global catastrophes. Their pasts are intertwined, And now, their futures depend on the health of the one planet they share.